In October of 2017, a telescope in Hawaii picked up a point of light moving through our solar system at a trajectory that meant only one thing: it had come from somewhere else entirely, drifted across the emptiness between stars, and was now passing through our solar system on its way back out, never to return. A fact confirmed almost immediately once astronomers ran the numbers on its exact path. Astronomers had less than a couple of months to study it before it faded from view forever. And nearly 9 years later, despite one of the most intensive scientific investigations ever conducted on a single object this small, researchers still can't fully agree on what it actually was. Stick around, because I'm going to walk you through exactly what made Oumuamua so strange, why the most popular explanation still has real scientific skeptics, and why this one object continues to shape how astronomers prepare for whatever comes through next. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the far edges of our solar system. To understand why Oumuamua generated this much ongoing scientific disagreement, you first need to understand just how unprecedented it was the moment astronomers realized what they were looking at. Discovered by the Pan-STARRS Survey Telescope on October 19, 2017, it was immediately obvious from its orbital path that this object wasn't following a closed loop around the sun the way every comet and asteroid native to our own solar system does. It was moving on a hyperbolic trajectory, meaning it arrived from interstellar space, swung once around the sun, and was already on its way back out permanently. It became the first confirmed interstellar object in recorded astronomical history, and researchers named it Oumuamua, a Hawaiian word roughly translating to scout or messenger, chosen specifically to capture the sense of something arriving from a great distance to reach us first. The problem was timing. By the time astronomers confirmed what they were looking at, Oumuamua had already passed its closest approach to the sun and was rapidly speeding away, giving researchers only a narrow window of a few weeks to gather as much data as possible before it became too faint to study in any further detail. Every telescope capable of contributing useful data got pointed at it during that brief stretch, and what came back left researchers with more open questions than confirmed answers. The first anomaly involved brightness. As Oumuamua tumbled through space, its brightness varied dramatically and repeatedly, changing by roughly a factor of 10 over the course of just a few hours. That kind of extreme variation typically indicates an object with an unusually elongated or flattened shape, tumbling in a way that alternately presents a larger and smaller cross-section of reflective surface toward Earth as it rotates. Detailed analysis of that brightness pattern, carried out by researcher Sergei Mashchenko, produced two possible best-fit shapes, either an extremely elongated cigar-like form with proportions roughly 8 times longer than it was wide, or alternatively, a flatter, more pancake-like shape with a less extreme but still unusual ratio. Either possibility described a shape genuinely unlike any asteroid or comet ever previously observed anywhere in our own solar system. To put that shape into perspective, nothing in our own solar system's catalog of tens of thousands of tracked asteroids and comets comes remotely close to matching those proportions. Most rocky bodies tend toward roughly blocky or moderately elongated shapes, shaped by billions of years of collisions and gravitational settling into forms that rarely stray too far from something resembling a lumpy sphere. An object stretched to 8 times its width, or alternatively flattened into something closer to a pancake, immediately raised questions about how such an extreme shape could have formed and survived intact across what was presumably an interstellar journey lasting many millions of years, exposed the entire time to the slow-wearing effects of cosmic radiation and occasional microcollisions with interstellar dust. If you're finding this as strange as researchers clearly did at the time, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. The second anomaly was almost the opposite kind of puzzle, an absence rather than a presence. When any icy comet approaches the sun, warming ice on its surface should sublimate directly into gas, producing a visible surrounding cloud called a coma, and often a trailing dust tail, the same basic process responsible for every dramatic comet tail ever photographed streaking across Earth's night sky. Researchers pointed some of the most sensitive instruments available directly at Oumuamua during its close approach, specifically searching for any trace of this kind of outgassing activity, and found essentially nothing. Multiple independent observation teams placed extremely strict upper limits on any dust or gas being released, well below what any known comet in our own solar system produces. Based on that absence, researchers initially classified Oumuamua as an asteroid rather than a comet, a rocky body without significant ice content, rather than the icy visitor many had originally expected an interstellar object to be. That initial classification carried real theoretical weight of its own because it fit reasonably well with a specific prediction some astronomers had already made about what interstellar objects should look like on average. The reasoning went that any icy body ejected from another star system would spend an enormous amount of time drifting through the cold vacuum of interstellar space, potentially hundreds of millions or even billions of years, during which cosmic radiation would slowly bake away and destroy the most volatile surface ices, the same materials responsible for the dramatic comas and tails seen on comets that spend their entire existence, closer to a star's warmth. Under that reasoning, an interstellar visitor arriving after such an extraordinarily long, cold journey might reasonably be expected to show up looking more like an inert, rocky asteroid, with the more delicate ices either stripped away entirely from its surface or buried too deep beneath the protective outer crust to sublimate detectably during a single brief pass near the sun. That classification held for only a matter of months, because a third anomaly then emerged that seemed to directly contradict it. Careful tracking of Oumuamua's exact trajectory revealed that its path couldn't be fully explained by gravity alone. There was an additional, small but measurable non-gravitational acceleration pushing the object away from the sun, roughly 1/1000th as strong as the sun's own gravitational pull, and following a pattern that weakened with distance in a way broadly consistent with outgassing, the same physical mechanism responsible for pushing ordinary comets around as they vent gas into space. Researcher Marco Micheli and colleagues, publishing their analysis in the journal Nature in 2018, concluded that outgassing remained the most physically plausible explanation available, but flagged serious caveats even in their own paper, since this would require Oumuamua to be releasing gas at a level that should have been detectable to instruments that had specifically searched for it and come up empty. This is exactly the kind of contradiction that made Oumuamua such a genuinely difficult scientific puzzle rather than simply an unusual but explainable visitor, an object accelerating in a pattern that looks like cometary outgassing, but showing absolutely none of the visible gas or dust that outgassing is supposed to produce. Physicist J.I. Katz, publishing a skeptical analysis of the original acceleration claim, pointed out that the implied ratio of gas to dust in whatever was supposedly being released would need to be at least 100 times higher than anything ever observed in a known solar system comet, essentially requiring Oumuamua to be made of an almost impossibly clean form of ice, free of the rocky, dusty material that every previously studied comet nucleus contains at least some amount of. Faced with that contradiction, researchers spent years proposing increasingly specific and creative explanations, each one trying to identify a particular kind of ice that could outgas efficiently enough to explain the acceleration while remaining chemically invisible to every instrument that looked for it. Astronomer Darrell Seligman and colleague Gregory Laughlin proposed in 2020 that Oumuamua might be composed largely of solid molecular hydrogen ice, sometimes described as a hydrogen iceberg, a material so different from ordinary water or carbon dioxide ice that it could theoretically outgas efficiently enough to produce the observed acceleration without leaving behind the kind of dusty residue standard comet models predict. A separate research team, led by Stephen Desch and Alan Jackson, proposed instead that Oumuamua might be a fragment of nitrogen ice, chipped away from the frozen surface of a Pluto-like dwarf planet orbiting some other star entirely, ejected into interstellar space by a violent collision with the specific properties of nitrogen ice potentially explaining both the unusual shape and the puzzling acceleration together. Neither of these specific proposals held up especially well under further scrutiny. Follow-up analysis suggested a pure hydrogen iceberg would likely have evaporated away entirely long before ever completing an interstellar journey lasting potentially hundreds of millions of years. And the nitrogen ice fragment hypothesis ran into its own set of theoretical difficulties, explaining exactly how enough nitrogen ice could plausibly be produced and ejected from a distant exopluto in the first place. Each proposal added something genuinely useful to the broader conversation, but none of them fully resolve the underlying contradiction on their own. The explanation that's gained the most traction more recently comes from a 2023 study led by researcher Jennifer Bergner, working with Seligman, published in the journal Nature. Their proposal doesn't require Oumuamua to be made of some exotic, rarely seen ice at all. Instead, it starts from something considerably more mundane, ordinary. Water ice, the same basic material found throughout comets across our own solar system. Bergner and Seligman's key insight involved decades-old laboratory research from the 1970s through the 1990s, largely overlooked in this specific context, until they revisited it, showing that when high-energy cosmic rays strike ordinary water ice over long periods, that radiation can convert a meaningful fraction of the water, potentially a quarter or more, into trapped molecular hydrogen gas embedded within the ice structure itself. A comet-sized object drifting through interstellar space for millions of years would accumulate exactly this kind of cosmic ray exposure, slowly building up a reservoir of trapped hydrogen gas locked inside its outer layers. Then, once that object finally warms even slightly during a close pass by a star, the trapped hydrogen could be released in a sudden burst, providing enough thrust to produce the observed acceleration, while the underlying water ice matrix itself remains largely intact, rather than visibly sublimating into a detectable coma. This explanation elegantly solves the central contradiction that had stumped researchers for years: an outgassing mechanism vigorous enough to explain the acceleration, using a genuinely common material, but one that doesn't require the water ice itself to visibly boil away and produce the dust and gas signature that instruments had already ruled out. It's a compelling piece of scientific reasoning, and it currently represents the leading explanation most researchers in this field point to when asked what likely happened. It hasn't, however, settled the debate completely, and it's worth being honest about that rather than presenting this as a fully closed case. Some researchers studying interstellar objects have noted that Bergner and Seligman's own model acknowledges the effect should be concentrated in a relatively thin outer shell of the object, and questions remain about whether that specific mechanism can reliably scale up to produce forces consistently strong enough to match what was actually measured across Oumuamua's entire observed trajectory, rather than just in principle. And a small number of researchers, most prominently Harvard astrophysicist Avi Loeb, have continued to argue that other explanations, including the more speculative possibility that Oumuamua's unusual acceleration could reflect something artificial, an extremely thin, lightweight structure functioning something like a solar sail, catching pressure from sunlight itself rather than any outgassing mechanism at all, haven't been fully and conclusively ruled out either. It's important to be direct about where the broader scientific consensus actually sits on that particular idea. The overwhelming majority of astronomers who have studied Oumuamua's data consider natural explanations, and the hydrogen outgassing model specifically, to be by far the most well-supported account of what happened, while treating the artificial solar sail hypothesis as a considerably less probable minority position that most of the field doesn't find persuasive given the available evidence. Part of why this particular mystery has proven so difficult to fully close is a limitation baked into the situation from the very beginning, one that no amount of clever theorizing can fully overcome after the fact. Oumuamua was gone. Once it sped back out of our solar system in early 2018, it passed permanently beyond the reach of every telescope on or near Earth, meaning every single explanation proposed since then has had to work entirely from the limited handful of weeks of data collected during that one brief encounter, with no possibility of ever going back for a second, more detailed look. Ordinary scientific verification, checking a hypothesis against fresh data collected specifically to test it, simply isn't available for this particular object in the way it normally would be for something closer to home. That limitation is exactly why the astronomical community has invested so heavily in preparing for the next one, rather than continuing to squeeze every remaining drop of certainty out of Oumuamua's now 9-year-old dataset. The Vera Rubin Observatory, a powerful new survey telescope that began full operations in Chile in 2025, was specifically designed with wide-field, rapid scanning capability, well-suited to catching future interstellar visitors much earlier in their approach than Oumuamua was ever caught. Seligman himself has calculated that Rubin's survey should detect somewhere between 1 and 3 Oumuamua-like interstellar objects every single year, along with potentially many more visible comets like the second confirmed interstellar object, Borisov, discovered in 2019, which behave far more like a conventional icy comet, complete with a visible tail, an easier case than Oumuamua by comparison, but still a genuinely rare opportunity to study material from another star system directly. That increased detection rate matters enormously for the specific hydrogen outgassing hypothesis, because it converts an essentially untestable one-off claim into something researchers can actually check systematically going forward. If cosmic ray-produced hydrogen outgassing really is a common, widespread phenomenon among interstellar objects and even ordinary long-period comets from the outer reaches of our own solar system, Rubin's expanded catalog of future discoveries should reveal similar unexplained accelerations, showing up again and again across multiple different objects, with astronomers catching them earlier and studying them in far more detail than was possible during Oumuamua's brief, rushed visit. If that pattern holds up repeatedly across a genuine sample of objects rather than remaining a single unusual case, it would represent about as strong a confirmation as this particular hypothesis could realistically receive. The third confirmed interstellar object, 3I/Atlas, discovered in July of 2021, has already given researchers exactly this kind of additional data point to compare against Oumuamua's original puzzle, and its own trajectory has shown a measurable non-gravitational acceleration as well, one that multiple research teams have attributed primarily to fairly conventional outgassing of carbon dioxide and other common cometary ices. a case that, unlike Oumuamua, has come with a visible coma and directly measurable gas chemistry throughout. That comparison alone illustrates just how unusual Oumuamua's specific combination of traits, extreme shape, complete absence of visible outgassing, and measurable acceleration actually was, even set against the two other confirmed interstellar visitors discovered since. So what does all of this actually add up to? A tumbling, oddly shaped object from another star system passed through our solar system for a matter of weeks back in 2017, left behind a genuinely contradictory set of measurements that took researchers years of careful, creative theorizing to even partially reconcile, and still hasn't been fully, unanimously explained to the satisfaction of every scientist who's studied the data. There's something worth sitting with, and just how much scientific effort has gone into fully explaining a single object smaller than a large building, one that was only ever visible for a matter of weeks, nearly a decade ago. Dozens of research papers, multiple competing hypotheses spanning everything from exotic hydrogen icebergs to fragments of alien dwarf planets to decades-old cosmic ray chemistry. Nobody had thought to apply to this exact problem. And an entire next-generation observatory partly justified by the need to finally get a second, better data point. That level of sustained attention isn't really about one unusual rock. It's about what a genuinely anomalous result, one that resists easy explanation, can teach an entire scientific field about the limits of its own existing models, and about how much can still be learned from a visitor that was only ever going to pass through once. The most well-supported current explanation, cosmic ray-produced hydrogen trapped inside ordinary water ice, is a genuinely elegant piece of science, built on decades-old laboratory work nobody had thought to apply to this specific problem until researchers went looking for exactly the right overlooked clue. Whether that explanation turns out to be the final word, or whether the next interstellar visitor Rubin catches reveals something that forces astronomers to reconsider the puzzle all over again, remains to be seen. If stories like this one, grounded in real published research and honest about where genuine scientific disagreement still exists, are what you want more of, subscribe to this channel and turn on notifications, because there's a real chance the next interstellar object confirms this explanation for good, or reopens the whole mystery in a way nobody currently expects. Thanks for watching, and I'll see you in the next one.